Well, hello, everyone. This is our podcast. What I have here today, whom I have here today, a little correct grammar. Nothing is scripted. You're going to find out. We're going to be full of mistakes or not. What I have here today, whom I have here today, is Connor, who specializes in consciousness work with regards to IRIS-AsteronX, and Daniel, who specializes in biology.
Yeah.
Also working with us. And on that note, we have a couple of topics to talk about. We tend to follow a lot of squirrels. That's a good thing.
Yeah. And
we
tend to also think beyond our professions, or studies in a logical manner where it cross applies.
Yeah, there's so many topics bleed from one to the other. I was just talking to them about a flotation concept. The overall concept, I was applying it to engines. So whereas one subject has a relevance to another subject, is so common.
Yeah.
So today we are going to touch on what I refer to as the modal moment. This is a ZPE energy extraction.
Yeah.
We'll talk a little about what that means, what it is. I also want to cover magnetic levitation by Lorentz force, what it might be. We're going to touch on time travel, and we're going to give you an introduction to a new kind of engine, Macron propulsion, which I am going to be creating a video about, so you'll get a more long-winded version.
And let's hope is it gonna be like similar to the videos you have made in the past for other propulsion systems? Right?
No, it's going to be more like the two newer ones.
Okay.
Okay, so, and here I'm replying to somebody here.
Yeah, we're also on Discord at the same time.
Yeah, we have people sending us messages, yeah.
Yeah.
Okay, so, and yeah, you're okay, Connor. I can't hear the construction.
Okay.
And you can actually speak that out. I don't mind recording that. That's fine.
Okay.
Okay, so the first topic here, I need to scroll up. The modal moment. Okay, let's talk a little bit about the modal moment. What I'm going to do here is I'm going to throw in a QB. I'm going to give it a couple of lines. This is a very, very basic model here to give our audience an idea of what it is.
It's completely flat, right?
And how it works. Yeah, no, not exactly, but this works because we're going to go.
Well cut it into. Yeah, you might as well cut it into 4 sections, according to the diagram. Yeah.
Yeah, it will. Yeah, that's. Yes, I've already been somewhat pedantic today when we were talking, going over the top, making too many details, but I want to steer from that because we have a couple of different topics and only 2 hours to really cover it in. So let's see.
Colors.
Okay, so the modal, and it's kind of like chewing gum and walking at the same time.
Yeah.
Let's go to the other side. No, it's still not showing the lines. Excuse me, audience. Bear with
Let's
me.
contrast the colors.
I
yeah.
need more contrasting colors, yeah. Maybe do I have something glowing that'll give it contrasting? Yeah, I do have some. Let's have some glowing red. Ooh. All right.
Yeah, that looks like it.
This is a very, very basic idea of the modal device. The modal device is it's a device with this gap. This represents a gap between dissimilar materials. It's a cavity, and this cavity. Why did I make it a cavity? Huh? Wouldn't that make more sense? And then I can make these. Yeah, that's a better idea. If I make these defined lines like that. Okay, I think that works
The
better.
boundaries. Yeah.
Yeah, I want to make sure they can actually, our audience can see. All right, so the modal device is he calls it a 0-point energy extraction. This is Professor Garret Moddel at the University of Boulder in Colorado. 25 years, him and his team have been working on this. Garret knows what he's talking about.
Yeah.
The way, in essence, the way this works is this 106 nanometer gap. The perturbations, which is to say the total disruptions in the quantum vacuum, which is a medium. Space is not made of nothing. It's made up of energy and matter, which is analogous to energy. It's just, albeit condensed energy. Matter is condensed energy. But the universe not only has matter in it, but it has energy in it, whether it's electrons 1 per square centimeter on average, or whether it's gamma rays, it's beta rays, you name it, alpha waves, just all manners of mostly deleterious, meaning dangerous energies. But all of this perturbs even the rotation of the moon, the earth, the sun. I mean, think about the sun constantly just pouring out energy. Bloop, bloop. Yeah, it sounds like that too, right? No, just kidding. But all of these things, including supernovas that might be a light year, might be several light years away, whether it's quasars, whether it's the galaxy in motion, colliding galaxies, basically, if you can think of it, it's pretty much happening out there. Even if it's ET flying through the universe, he or she is still perturbing the energy of space. This is what we call the quantum vacuum. Take a pan of water and 2 wooden stirring spoons and just beat that water until it's out of the pan. That's analogous to what the quantum vacuum, what's happening within the quantum vacuum. All these actions are just beating the drum of water. And so what's happening is that Garret Moddel's device is taking advantage of this pressure. So imagine for a moment that on the right-hand side is all this perturbation, all this motion. And on the other side, he creates a gradient, an energy gradient. Yes, the perturbations are, you're going to say, oh, well, they're everywhere, all around it, and you would be correct.
Can I add in?
Yeah, go ahead.
In the center, it's calmer, so to speak, because some wavelengths are excluded. The gradient is the relative noise between the outside and the inside of the
exactly
device, right?
Exactly. Yeah. You're right. So between all of this on the outside, and That's a better way to describe it than how I was going to describe it. Thank you, Daniel. So, as Daniel was saying, the perturbations that exist all the way around within this little narrow gap, 106 nanometers, it's relatively calm. On the outside, it's loud, noisy, and obnoxious, so to speak. And inside is more of a calm, quiet, sunny day. And the reason why is because this gap here disallows higher, longer wavelengths, so that it physically disallows the longer wavelengths. So you have a quieter space.
And if people would also like to know are these wavelengths that are just traveling, that are photons traveling through space from some source, or is it just an inherent property of space that it has these waves in them? My explanation is that it's both, but it's largely the inherent property of space, right? Itself.
Okay, so if you imagine for a moment that the pan of water, the water molecules in the pan represent all of the energies of space.
Yeah.
And that means you'd have a whole bunch of different kinds of water molecules, so to speak. Mm-hmm. If you take your drumsticks or your wooden spoons and you just beat on that water, it's an open pan of water, and you just beat on it, what's going to happen to the water?
It'll be choppy.
Yeah, very choppy.
And if we then put two ships on that water next to each other, parked, they'll be calmer in between them, and they'll probably be drawn together too.
Yeah, if I take and actually make a quick little model of that, this is basically what I've been doing in the newer videos. So if I take this, make my pan of water.
Yeah.
And now
you're gonna make the water too. You're gonna make everything rather than just the two ships. Yeah. Okay. That's good.
Yeah. Gee, I know there's a modifier that I can put on that.
Probably we're gonna need these models pre-made.
Yeah, but I don't want to. We have time constraints, so let's see which one was that. Yes, I'm not an expert in Blender. I'm pretty good, but I'm not an expert. Let's make this. The height is a little bit too big. We just made a speaker.
Be careful because I don't know what software were you using when you were making those other epic videos in the past. I thought it was Blender.
It is Blender, yeah. Oh wait a minute, not Wave. I think there's an Ocean one. The form. Did I miss the Ocean?
I just make a solid surface with two objects in it. Yeah.
Am I missing? Well, maybe it is Wave. Surface to form. Warp. No.
So this is like a software demonstration as well.
This is showing you how much I know about Blender. Okay.
It kind of shows how much time you spend at the blackboard, so to speak, not on Blender over the years. You have more blackboard experience with physics.
Yeah, it's we're gonna do it without any further ado. We're gonna do it a little bit differently here.
It looks like yeah.
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 Oh, it looks pretty. It looks pretty. That's it. It doesn't really look good at all. It looks kind of rude, really.
I get the frequency up, but right
Okay.
now you got an empty spot in the middle to put plates
Do I have
in,
any?
but-
Let's make it blue. And all right.
Bumpy water.
Yeah.
I hope you guys can see past my my limited water capabilities here. All right, so now imagine for a moment, and hopefully this is visible enough on screen too. Okay, so if I now take a plane and I bring it over and I'm going to divide the water.
Yeah, this also goes to show, right, how much effort it took to make the old set of videos.
Oh yeah, our videos were definitely really long-winded. And actually, this is not what I want to do. Well, it is. Excuse me. It is what I want to do, actually. Because when I do this, you need to be able to see it. Because I'm going to have 2 plates. All right. Now, the gap that we have between these, I'm trying to go too fast here. Haste makes waste. Young man.
Yeah.
Okay. Now, this is analogous to the Casimir plates, which is the same thing we're talking about with regards to modal's device. Because these blobbies, represent a wavelength, the physical size. A wavelength is analogous to the physical size of the wave. And if and please don't say, you guys, that this wavelength, I'm gonna eliminate it. This wave right here shouldn't actually, well, no, actually I am gonna leave it there because it illustrates something else. Okay, this wavelength, this wave is too big to fit in here. And what you're seeing here is a tiny aspect of this whole wave, which in reality would not be allowed to be in here.
Yeah,
so
that would be excluded.
It would be excluded. So what I'm going to do is go ahead and exclude that.
We can also say that there are more bumps or waves outside the plates than inside. Therefore, gradient is still technically explainable.
Okay, so if I explain it this way, all right, only the smallest of waves, perturbations in the water or in the space-time, because this blue water represents space-time, only the smallest of frequencies, wavelengths, can fit between these 2 plates.
Yeah.
Only the smallest. And that is the analogy with regards to the modal device.
Yeah. And there are wider implications here too, right? Because remember how in their videos, guys, it says that the vacuum fluctuations permeate everything. And how come they don't permeate the material of the plates? That's something interesting to figure out.
Because they don't permeate everything. And it's not entirely, it's a yes and a no. But let's get back to the modal device, then we'll jump to what you were just talking about in a second.
Yeah.
You see, the Casimir plates are conductive. And so the part of the quantum vacuum that cannot penetrate the EM spectrum is quieted. So between the two plates, it's less positive. We're familiar with energies outside of and around us everywhere that are positive energy. We experience it. And your car is positive energy, your desk, your computer, your cell phone, it's all made out of positive energy. You can interact with positive energy. You cannot interact with negative energy because it's tachyonic. I'm not talking about antimatter, which is not negative energy. It may have a negative, it does have a negative arrow of time, but it still falls in a gravity field. It's still interactable. Therefore, it's positive energy. So Modal's device calms the storm around it. And therefore, as a result, it creates an energy gradient outside of itself with respect to the inside. And in case someone's confused here, let's go ahead and cap these ends, because it's a closed system. Just so that you guys can see.
Closed.
Yeah.
I thought it had to be open. But I mean, I need to open my definitions.
Oops, I didn't to the right. Hold on a second. I was expanding. So why I'm being somewhat a little bit pedantic about this is because I'm trying to give our audience as clear and basic an understanding, for not because they don't understand, but because we don't no two human beings really think alike. And by giving multiple examples, for those who are kind of like left shaking their head, I don't quite get it. It's my hopes that they will get it. They'll understand. So for those of you who do get it, yeah, well, stick with me, bear with us. If you take a cannonball and you hold it up over your head, what have you done? You've imparted kinetic energy to that cannonball. So the moment you, relative to the ground, so the moment you drop it, the moment you raise it up over your head, you've given it potential energy, kinetic energy, with a potential to fall at a given rate relative to Earth's gravity. So the moment you let go of it, you watch the ball fall through the gradient, the energy gradient generated by you raising it up over your head. Well, that is analogous to why we say that there's an energy gradient outside of Modal's device relative to the Casimir gap, the 106 nanometers. That means that you have outside pressure trying to push these, trying to close this little gap, positive energy gap pressure. So if you take our analogy of our pan of water, the water out here and out here will try to force these two plates together. And as it does so...
Hold on a second. Connor?
Yes.
Your indicator seems to be pulsing. Can you mute? Maybe it's going to be recorded, your noises.
Are you guys able to hear the construction outside?
No,
I'm not
no,
hearing
but
it.
the software might when it's posted. So yeah, probably would be advisable to block that out.
If it does, I'll throw a filter on the system. And I don't think you really need to be concerned about it.
Okay.
Because I think it would be better if you were in it, unmuted.
Yeah.
But, I mean, it's up to you. It would be no big deal either way. Okay, so, and I'm a little bit preoccupied my explanation. So the perturbations, the waves of the water on either side of these two plates will try to force these two plates together. It's like when you run a small boat down through the two bigger boats, you create a partial vacuum in the water, so to speak. You create you perturb the water in the middle, and you cause the two boats to want to float together. And sometimes, if it's strong enough, it'll crush the small boat in the middle. That's an energy gradient. So the pressure on the outside relative to the inside creates this energy gradient towards the center. That's why these two plates will be forced together if there's nothing to stop them. Well, in Model's device, these are physically connected, and therefore they cannot be forced together. And therefore, there's a persistent energy gradient. And by tickling the pressure on the outside of these two, an electron will appear between these two plates. And it works. Model's device does work. It actually creates, a quad array is able to create 480 watt hours. Yes, Dan.
From what I understand is he puts in laser light photons to do the tickling.
Yep.
And because of the size of the gap, it has to be like in the UV range, I believe.
It's in his paper. Yeah.
Yeah, and then the electrons get, because of the walls probably are moving back and forth a little bit. The electrons get excited, and then you can draw current from that more than what the laser provided.
Yeah, this is very, very basic analogy, and if I understand what you're saying there, how you explained it, I would say yes. It's kind of like, okay, here's the bowling ball you put over your head. You're holding it there. All right, so if someone comes up and tickles your arms, you're going to drop the bowling ball. And then the bowling ball will fall and hit the ground with a force relative to its weight, maybe 75 pounds. And that is a very, very basic analogy of how an electron is created, or not created, sorry, how an electron is what exactly does happen here? An electron comes off of the material.
Yeah.
Not inside of it, but an electron. I mean, think of all the atoms that makes up the device.
Yeah.
There's a lot of electrons bound up in there.
Yeah, so this could be related to the material's work function, where it has enough energy to put into the electrons, where it could
But there's
break
electrons.
the energy bond between the.
There's plenty of positive energy, including electrons, on the outside of the device as well. And so we know that metals are conductive. You can get plastics to be conductive if you dope them with arsenic. Then they become conductive. They use that. They actually make wires for aircraft. Doping it with arsenic makes it conductive. The plastic is lighter weight than the alloys. But okay, so but there's no gaining an electron without some sort of payment of energy. And Model's device does have a net positive energy out relative to the energy in, because it's not operating as a closed loop circuit. Aha! Where's it open? Where is the open-ended to? Well, now that is actually where the key lies in his device being able to function. If you looked at the universe as being only merely mechanical, then you'd have to throw out all quantum shenanigans. You'd have to throw out all of quantum reality. That means you'd have to throw out entanglement. You'd have to throw out spooky action at a distance, which is entanglement. Excuse me. You have to throw out the fact that we observe particles appearing and disappearing. You'd have to throw out the double split experiment, on and on uncertainty principle, but all say goodbye to it. If the universe was strictly mechanical, non-tachyonic, is what I'm saying. In fact, the reality of the universe is that it is more quantum, meaning tachyonic, than it is mechanical. Mechanical, aka positive universe. Quantum, aka negative universe. The two work in tandem. Let me say that again. You cannot have one without the other. The two work in harmony to create what we see and experience on a daily basis. So Model's device must make use of the quantum realm of reality and the mechanical aspect, aka the electron. So in order for him to gain an electron, his device is quantum mechanically paying back energy, conservation of energy, in a quantum fashion. So at some point, I'm very likely to make a video where I break this down. Don't expect it too soon. It might be 6 months, maybe a year, in fact, away. I'll try to make it sooner. And we have many things to do, not just creating videos. Although this is fun. Connor, Daniel, do you have any questions that might help our audience? And audience, if you guys have any questions, throw them in the comments below. Please don't make it a long-winded comment. I have a lot to do. I have a lot to do.
A question I was going to ask is, when looking at Model's device, right, you were talking about how the gradient being created allows for an added electron to be obtained. And I think that the actual components to his device kind of illustrate that pretty well. Also,
it does. Yeah.
And so could you explain how the setup he has with his different cathode anode plates, I believe is what he's using.
Yes.
And the wiring to that, how that takes advantage of the quantum pressure.
Okay, so the gap, if I'm understanding your question here enough, the gap itself, we were talking about the fact that the gap quiets. This in this gap between these two plates is less positive energy than the surrounding outer realm, which sets up, like the pan of water, it sets up a natural gradient, which I represent with this slope here. If this was a chart, you would have a gradient of energy from, say, 0 baseline to 100%. This is an energy gradient. The cannonball currently exists at the 100% potential kinetic energy, as opposed to being on the ground at baseline. 100% baseline. So this is an energy gradient, which you can represent this way or this way. And on the chart, you might represent it like this. Ground, 100% potential. So these are conductive, and Model's plate with the dissimilar, this is why this dark area, which, sorry, I didn't explain this. This is a different kind of material. Different, it's a metal, conductive, and this is conductive. But in the middle, it's non-conductive. You know, I thought I had a better understanding of how the device was built. I'll have to reference it and break it down when I do make the video about it. But
you mean you thought you had a better way to explain it?
No, this is not entirely 100% accurate. It's a very basic, general depiction of the device. Yeah,
the real device's plates look more like a diamond.
I'm going to do a search right now on Garret. No, it's Garret Moddel's device. Let me go ahead and see if I can bring up a picture and drop it into Blender. Garret Moddel ZPE is what you search. And then his video. He has a couple of different videos. So let me go ahead and search it, because he shows an actual electron microscope image of the MIM device. Okay, so let me do a screen capture. Okay, bear with me. You guys should start to see it now. Or you should see it on the screen now.
Mm-hmm. Yeah.
Yeah.
So let's go ahead and let's
shift it over.
1 second. I'm going to hide my device.
Yeah.
And then I'll bring this up. This is Professor Garret Moddel, everyone.
Yeah. You're at the top right.
At the top right. Above the cannonball.
Yeah.
Yeah.
So he has lots of potential energy. Okay. So this is Model's. Oops. I need to hide my device.
Put it behind the screen, yeah.
It was behind, but it popped forwards. Okay, so at the moment, what his materials are made out of is right here. This is the breakdown of his device.
That's one of the views, that is.
This is his diagram from his video. We'll put a link in the description below. This transparent dielectric material is the 106, the optical cavity. That's the gap here. And by having it at a transparent medium, what that means is that it limits the potential positive energy further still. Now, let me emphasize on that. It's not negative space yet, but it's less positive.
Yeah.
You can, all of the area around you, and your arms, your computer, your cell phone, your laptop, desktop, notepad, whatever, that's positive energy. All of the space within your body is positive energy. It's positive energy and positive space. But Garret is, because of this narrow gap, creates a less positive space. Now, of course, we're going to go in a little squirrel. All throughout your body are microtubules. Microtubules. And those microtubules, within those tubes, is less positive. So there's less positive energy, is what I'm saying, inside the tubes than there is outside and surrounding the tubes. And all throughout our bodies are microtubules, which are important for the function of our organs and otherwise, including important relative to our consciousness. That's another topic, which is why Connor has joined us, specializing in consciousness, and Daniel specializing in biology, is because we're incorporating all of this into our space project, which we're creating.
Biology is pretty interesting because it has we have several structures inside of our cells that we don't find in other materials and objects and stuff, and that's kind of suspect because it's when you have flat pieces like molecules, like DNA bases stacked on top of each other, as well as the other example. Flat, like tubes with flat surfaces where they're like, because diameter wise, it's suspect because it looks like this, right?
And hair, by the way, is a microtubule. And on that note, back in either the late 40s or the early 50s, the U.S. Army hired, I think it was a pair or a trio of Native American Indians with their long hair. They happened to be specialists in, like manhunts. They could track. They could track whatever. They could track humans, animals, you name it. Well, they were so successful that the Army brought them in so they could train others. And the first thing the Army did was cut their hair off. The first thing that they could no longer do was track humans.
You know why the Army does that? I was in the cadets.
Well, we know why. You grab onto your hair in combat.
I think they were trying to
conformity.
Yeah. They didn't know.
Yes, sir. No, sir.
In cadets as well, everybody had short hair, females included, and it was for logical reasons, right? The equipment and stuff. You don't want to, you're out in the bush in the heat. You don't want to have thick hair, and stuff like that on military bases.
Yeah. Now we're not saying. I got to throw in a disclaimer. We're not bad mouthing the military. They didn't know. They had no clue, and neither did the Native American Indians.
Nah, I'm not.
But this is
possible.
This is evidence. I'm sorry.
Yeah, it's not possible for us to badmouth the military because we're in all different countries and it's all the same everywhere.
We're not bad-mouthing at all, no. And conformity is necessary, because if you're out there on the battlefield and one person says, I don't really feel like defending my comrades today, or my coworkers, or whatever. I don't feel like covering your six today because I'm having a bad day. I broke a fingernail. I mean, just whatever it is.
Stick out like a clown?
In other words, my point is,
sorry.
I think everyone understands the militaries there's a necessity for it, because consciousness is not at a level where we have no wars, no conflict. And so therefore we need to be able to defend ourselves from psychopaths and others. That's just the way it is. So and I have no more. I don't need to say any more about it. Let's get back to the modal. Connor, did I answer your?
It's a resource. It's because of resources. So this modal device could serve as a measure to maintain security and resources and access to resources. So therefore, you don't need any war after this gets adopted system wide.
It would certainly. Okay, so the modal device he has over 1,000 test devices that function. Mm-hmm. It's not someone in their garage or basement, which is still legitimate. It's not someone in a lean-to. Excuse me a second, Daniel. It's not someone in a lean-to with a tinfoil hat that is making claims so they can have the limelight on YouTube or somewhere like that. Yeah. This is a tenured professor who has all the equipment and knows darn well what he's talking about, who has made precision devices. And
precision, yes. Not garage.
He has, let's face it, personal computer was invented in a garage. So there's nothing wrong with a garage. I did my own experiment, actually did it in my bedroom, and was successful with it in the late 80s. So that was my first introduction in making experiments that function. Okay. The point here is that Modal can prove that his device works. Anyone who wants to interview him and go to his location in Boulder, Colorado, I'm sure he'll be glad to provide the interview and the demonstration. The fact that his device produces a quad array, that's 4 connected together, can produce 480 watt hours. That's nothing to sneeze at. That's phenomenal. What it means, we crunched the numbers. A battery pack, or a modal pack, I'm calling it, this is my own terminology. We call it here in-house a modal moment. It's still a 0 point, or it's a quantum. What this is a quantum reactor. Literally.
Yeah, you took my name for it. Yeah.
It's a quantum reactor. So
exactly.
But I call it a modal moment because that term has the ability to stick. And when you associate it with quantum reactor, bingo, everyone knows what you're talking about.
Yeah.
So when you put it, one second, Daniel.
Okay.
Because I was on a flow there, going somewhere with it. When you take those quad arrays and you combine them into something about the size of a Tesla battery pack. The Tesla car no longer requires being recharged. You're still going to require some batteries in order for this device to charge those batteries, but you no longer need to charge at a station. The modal device does not run dry. It doesn't draw enough energy to deplete the quantum foam, the quantum vacuum. There's 3 different names for the quantum vacuum. The quantum foam better illustrates, you beating on the pan of water perturbations. So that's why we call it, this is more, if you were to take your drumsticks and really beat the heck out of this water, it will look like foam. You will generate foam. So Model's device makes use of this quantum foam, and in order to encourage electrons to appear. Okay, so one thing we didn't explain was the quantum foam. You see, this is not scripted. The quantum foam contains a huge amount of virtual particles, imaginary particles, which is in your mathematics, virtual numbers.
Yeah.
So what happens is that Garret Moddel's device makes use of a laser. So we'll use this gradient thing here, pretend that this is the laser. And so the laser zaps an aspect of the device, encouraging the manifestation of the virtual particles. And just for our audience to know that these virtual particles are not imaginary particles like you might have in your computer, like, this pan of water is virtual, meaning that it's only made up of within this confines of this virtual environment, to illustrate that these virtual particles are actually more real than just being imaginary particles. These virtual particles have already been proven by the MIT to move 40 kilogram mirrors in space. They've now proven that these perturbations, I can say this, these perturbations have moved 40 kilogram mirrors slightly out of alignment. And they have to compensate for that. And then there's another thing. Our modern satellites have tiny little nanocircuitries that are affected by the perturbations of the quantum foam. And so they have to have quantum waveguides that are there to dampen the perturbations of the quantum foam. Otherwise, they get random electrons in the circuit, which they just appeared. Now, when we know that particles come into existence, it's just you can go read about it in quantum physics. We've observed in the laboratory particles pop into existence and then pop back out of existence. And it's due to the quantum foam, which proves, we're proving here in science that what we call imaginary particles, virtual particles, are actually real. What's the difference between an electron and a virtual electron? One is half particle, half congealed. The other is a full particle. You could kind of say that one's half wave and one's full wave, just to make the point. And then the laser, a modal's laser, when it strikes the plate, it gives the impetus for the half electron to become real, to become a real particle. And then his device, because it's metallic, it's because it's conductive, sucks up the electron. And then the electron is then carried away by the fact that he has cathode anode.
Yeah. And somehow if extra electrons are being made, they have to also disappear then back and down. Otherwise, it could also be interpreted as a straight energy transfer. So energy gets transferred to electrons that already exist in the material. That could also be an explanation.
Because of the law of conservation of energy. Say that again. I didn't know you were asking me. I'm sorry.
I was asking a question that an alternative explanation is that energy transfers what's happening to electrons that are already in that device. Because your explanation is extra electrons are materializing and then flowing in the circuit, but then they also have to disappear on the other side of the circuit,
so
because
the virtual electron is going to appear. It's going to be realized either in the middle here, in the gap, or it's going to be realized outside. And you see, this is why I'm not going to make the video on this ZPE right now, because I need to study his device further in order to break down exactly how his device works. I'm giving the concept on how I think that the device works based on what I already understand. So just for our audience to understand, my hypothesis here is fairly sound. Whereas how he talks about it, how his device is configured, may have some conflict with what I'm saying. But I'm going to bet that the analogy I'm giving is correct. We'll see. I'm going to deep dive into that as the time carries on. But the virtual particle, which is half particle, doesn't have the impetus to be drawn in and attracted to the metal, to attach itself to the material, to the conductive plate. It's not a full particle. This idea of half particle and full particle is not new. That's not just my idea. That's already been theorized. And if someone's just going to reject all of this like it's all heresy, then you're not thinking about what you're saying. When the modal's device converts the half particle, gives it the necessary energy to become a realized particle, a full particle, then the device, the electron, can glob onto the atoms that make up the metal. And because now he has a charge, a net negative charge greater than it was, a greater potential on the two plates, naturally the electron is going to migrate to one plate as opposed to the other because it's a negative charge. So it's kind of analogous to using a Van de Graaff generator to charge a sphere. The sphere will gain a net negative charge, you can attach the other side of the Van de Graaff generator to the positive. So you have an anode and a cathode plate. And so the positive side will gain a positive charge with respect to the negative plate or the negative sphere. And same thing happens within the modal device. So you have a net negative charge gain, which relative to the positive side, there now can be a flow of electrons. So, is that clear? Do you guys understand the analogy thus far?
Yeah, and I would also say that if obviously Modal has this video where he shows how each component to his device in a really in-depth way
It does.
generates the electricity, and it's kind of the backbone to a lot of other ideas that AsteronX has had as using that as a baseline to do other tasks.
Yeah. His modal, there's several videos out, and Modal's videos are fantastic. And yeah, he really does know what he's talking about. And guess what I just did?
Oh, yeah.
I just put on screen the right here. This is the URL for his. But I'm going to put it in the link description below, in the video description below. The link description. So if you want to pause your screen, or you can just click on the link down below. Now that's, I didn't choose the share one. I think that's longer. Let me find out. I'll quickly do it. It's fun. Yeah, there we go. That's the share link. I'll put them both down below.
Yeah, it was funny how YouTube does it.
The S on this, by the way, means secure. That's what the S stands for, secure. Secure connection.
Yeah.
Okay. All right. Now, that is the ZPE. That's the modal device. Well, I call it the modal moment. I hope he hears that. I hope he.
Yeah.
Yeah.
I would like to say that when you say quad array, you mean 4 of those on the lower right next to each other.
Hence quad. Yeah.
Because
Exactly.
a lot of people are not scientifically literate, right? So they don't know what an array is or a quad, right? Except for a all-terrain vehicle.
Well, that's not necessarily a scientific term. Yeah, but it's a terminology used. Well, if you're in Italy, you know what a quadruporte is. If you quattroporte, that's an Italian Maserati, meaning 4. Wait a minute, something like that. If you're Italian, please help us. Put in the comments, what does it mean? I thought I knew. I opened my mouth. Hold on, my foot is in my mouth now because I started to say something I wasn't fully knowledgeable about. Ow!
Surprising. You're surprisingly flexible. Then
I'm flexible. Yeah. Sometimes I don't feel so flexible. Okay, so
the other thing is that everyone would be trying to pry us like, oh, how can this quad array work if they're getting? They can easily Google this, all right? If you're getting, this is Google's numbers, right?
Yeah.
5.3566 times 10 to the negative 10 joules per cubic meter. So people are like, oh, how are you getting hundreds of watts per square meter, which is less than a cubic meter, of course.
Yeah.
It's a one dimension less. How are you getting that much when you're getting not even one normally? And the way this happens is there's a refresh rate of the quantum vacuum. When you take that unit of energy away, right, it comes back very fast, but you can't take all of it, right?
You mean,
but it is, but it's a lot. Right?
You're talking about depletion of the quantum vacuum, the hot quantum foam?
Yeah, how it's so much that you can't deplete it, actually.
Okay, so there is enough. The quantum foam contains, as I think it was Arthur C. Clarke that coined, there's enough to boil the oceans over and over again, some 10 times, or no, it's greater than the palest ghost. I already said in one of the videos.
I think you're conflating two things. I think it was Wheeler that said that you could, with a cubic centimeter of energy,
boil the earth. Yes.
No. Yeah.
Yes.
Several times
right.
over.
Correct.
Like 10 times or more. And
correct.
Yeah. And that adds up. If the refresh rate is really fast, like on the high end of the scale, like close to a Planck time.
Well, think about why it would be that way.
Mm-hmm.
Because when you have so many things in the universe perturbing the foam, the medium, which is something I didn't actually get to expound upon with our audience. If you consider the earth, the ground, is one of the densest materials. If you take a, granite,
you will live on,
or a block of lead, it's very dense. If you take and you put water on top of the ground, on top of the block of lead, providing, I'm not excluding porousness in the ground. Let's just say it's compacted. The water is going to sit on top of the ground, on top of the lead. That's because the ground is denser than the water. Both are the ground is a medium, meaning that it's made up of stuff. The water is a medium, albeit less dense than the ground. The water is still made up of stuff. Now, if you could get water to just sit there on top of the ground, and then you take air and you put it on top of the water as if you could, and that it would stay in place, the air is still made up of stuff. We call that a medium. And it'll sit, because it's less dense, it'll sit on top of the water, which sits on top of the ground. Now, if you took a blob of space, you could sit it on top of the air, because space is less dense than the air. The air is less dense than the water, and the water is less dense than the ground. Yes, we're talking about
material-wise. Now, when we do the energy density, then space is at this energy density, and then the air is space plus air.
Yes, of course.
It's more dense.
Yes, and I'm not talking about the energy density. One could argue and mathematically illustrate that the ground, which is made up of matter, which is analogous to, matter is made up of electromagnetic energy. When you really break it down to the very smallest constituents, quarks, subatomic particles, they're just made up of energy. So what in matter is actually matter? You know what keeps your hand from passing through your desk electric fields. That's it. At the very, very smallest, you have the strong nuclear force, and the weak nuclear force, and then you have covalent bonds and yada, 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 yada. But getting back to my point, what you have is that the ground is denser than the water is denser than the air is denser than space. My point is that space is still a medium. We're fish in a fishbowl, is the analogy. If you truly could go outside without a protective warp bubble, intrablock, which means separate, intra meaning that your own block separate from space-time. If you went outside into a true void where there's no medium, you would cease to exist without a protective bubble, because there's nothing to maintain the laws of physics. So when you think in terms of the modal's device, when you think of terms of energy production, when you think of terms of the quantum vacuum, or when you think in terms of quantum mechanics, or the mechanical universe, everything is just its gradient of density, but it's also proportional to the amount of energy. Because even when we say, and this is important, Daniel, the next part, if I have a region, if you're looking at the screen here, if I have a region around this ship, we look at this and it's all positive energy. Where's the negative energy? You know, someone will say, okay, the ship's made of positive energy, the air, the ground, the sky, clouds, the ship. I mean, you know, it's all positive energy. Where's the negative energy? Is the negative energy maybe up there in space? No,
that's caveman logic. It's there. That's all around you.
What do you mean? I'm caveman too, aren't you?
No, I just...
We don't want to insult our cavemen out there.
The general explanation, like, oh, is it over there? Is it over there? No.
Yeah. No. Okay, so my analogy here, and so the question remains, where is the negative energy in our positive world?
Yeah.
Well, the negative energy,
all around us.
We'll use I'm going to do another analogy. Yeah, Blender isn't Blender so cool for this kind of stuff?
Speaking of energy, Blender is cool. It's clearly a device in there. Now, speaking of energy density, you were also saying you were about to say that neutron stars are like a feeble ghost compared to the quantum vacuum, right?
They don't even. It's analogous to a tardigrade sitting on the sun.
Yeah.
I mean, it's worse than that, because the tardigrade has no ability to affect the sun in any shape or form.
Yeah.
Maybe the analogy would be better: a tardigrade next to a massive black hole.
Yeah. So just so everybody knows this is, if that number that I said, the 5.35 times the negative 10 joule per cubic meter, if that one regenerates at the Planck time, then you have enough mass density, if you convert energy to mass, right, to approach neutron star densities, the lightest of neutron stars, right? Which is 1 times 10 to the 17 kilogram per cubic meter.
It has been calculated several times already, and they've gotten really close. But in order to get the truest answer, you need to take into consideration both halves of the universe, which is what I'm about to embark on right now.
Yeah. I'm just saying that the numbers we have now, they are aligning with neutron star densities, and that's telling. The lightest of which, but neutron stars are heavier than that. No, most of them. That means they come with unusual properties from neutron stars on up. These remnants, they have unusual properties, and we have alluded to that in other videos. And especially the singularity converter video, by the way, and why it's used. And if that density is like a ghost compared to the actual quantity of the quantum vacuum, then you know that there are at least there's one density upgrade to than 10 to the 17 kilogram per cubic meter, such as the density of a singularity, and then probably one step above that as well, and that's the true. So that according to my calculations, I don't know. I hypothesizing on 10 to the 40 kilogram roughly per cubic meter. That's big. So that makes neutron stars, and especially you, very ghostly.
If you were to power a massive array of gamma ray, high energy gamma ray devices, it's enough to cut a hole through the center of the Earth, which would cause the Earth to release the internal pressure, cracking the planet in half. Now,
yeah, it's a different topic. Yeah, the lava comes out.
I'm illustrating the amount of energy. If you could throw that device into the center of the sun and cause it to go supernova when it's only intended to be a red giant when it dies. So just for our audience to understand how much energy that is. But now
I'm confused as to what you just said.
Okay, well, I want to get on with talking about the negative side of the universe.
Yeah.
So if for you guys out there think that negative energy does not exist, then that means black holes don't exist. That means that new pulsars don't exist. Because the jets coming off a pulsar are not just positive jets of positive energy. They're also tachyonic jets. A black hole is not just positive energy. I mean, we already know that inside the black hole is negative space-time. And for those recent people who think that there is no such thing as three-time values, go study general relativity, because in Einstein's equation are just those figures. Inside of relativity, you have, and I'm going to go to my notes here.
Yeah, and just so you guys know, the higher when I'm talking about energy density, the higher the number is, the smaller the time interval, the regeneration time, which can happen through various ways.
Okay, so this is really important because a paper came out recently. Okay, relativity includes a negative space-time consisting of 3 time dimensions and 1 spatial dimension. Now, someone recently just made a video claiming that this was heresy. That person has no clue about relativity. I just want to put the record clear. Go study. your long career in science, you just threw the baby out with the bathwater. You see,
So Sabine is okay?
I didn't give any names deliberately.
Yeah. Yeah,
Now,
she covers this.
Okay,
stories.
well, that's fine, but I'm not going to give any names. I'm just saying that all right, I'm not gonna give a name, but I'm gonna say it this way. I'm gonna throw in another squirrel. You know why science is developing a bad reputation? Because science says, no, you can't do that. I'm coloring it, obviously. This is not very scientific, but I'm only making a point. Science says, no, you can't do that. I know what you can't do. You can't do this. You can't do that. We already know you're breaking the laws of physics. Well, wait a minute. Slow down before the diarrhea comes out of the mouth. What are you saying? I can't do this. You can't break the laws of physics. Are you telling me that you already know everything there is to know about the laws of physics in the universe? Well, you know something? For mainstream science to draw such idiotic conclusions is not scientific. And here's why. We don't know everything, and we have major problems in science that mainstream science cannot explain things we already observe. I'll give you one very good example, and hold on, Daniel.
I wasn't going to say much.
An electron orbiting around the nucleus. If the universe was strictly quantum mechanics, strictly mechanical, non-quantum, which we know it is quantum also, but if it was just strictly mechanical, then the electron was already calculated to have run out of energy and slammed into the core of the nucleus. This is a fundamental, unsolved unit. It's an unsolved question in mainstream science.
The way they solve it is, it is a quantum particle, and it's oscillating as a wave around
it's
the atom.
Magic wand waving. It's hand waving. Yeah, well, we're going to dismiss it. It's like the virtual particles, which they use. Mainstream science has always said, they're just imaginary numbers there to help you with your equations. No, they're not. They're telling you something. And if you open your mind instead of letting it fall out on the ground, then you'll see that we can do more with what we don't need to have magic UFO tech. What do you think UFOs fly on? Magic? Ooh, no. This is not magic. We don't know everything yet. And for mainstream science to declare that this and that is absolutely forbidden, they're basing it on the fact that we can use our physics to send a rocket to Mars and back again. And so they say, look, we've already proven we know what we're talking about. But you know something? We can't explain the electron orbit around the nucleus. So we know everything there is. So in two statements, they just pulled the rabbit out of the hat, and it's a virtual rabbit. It doesn't make any sense.
They just say that the electron just is spread out across the entire atom.
Okay, it still doesn't explain.
But they don't tell you why that is.
Okay, but this is why science is developing a bad reputation, because science keeps telling you that, well, if it's, because UFOs have a negative connotation, which is not a definite. Connotation is not the denotation. So science says, alien, UFO, it's all associated with fringe science, and therefore it's has no credibility, and I'm not even going to consider it because it's going to my boss is not going to pay me, they're going to fire me, and I've got to consider making money, not science, and and on and on and on. If I was 20 years,
the story sells better with the alien story.
Okay, so my point is this: we have a division between, mainstream science labels it fringe, meaning that it's magic, fantasy. And then on the other side, we have mainstream science that says, nah, you can't do that. They don't really exist. And when right there, you have polarization, and then you don't have there's no gradient. What you have is two inflamed situations. So science is losing favor with the public because it's ignorant, which is not a dirty word. Look up the definition. It's not a derogatory comment meaning to tear down science. It means that they're without knowledge. Ignorance, the definition, the denotation of ignorance is without knowledge. That's all. It's not, I'm not using it in a derogatory connotation fashion. So
is it also the resistance to step beyond your boundaries also is ignorance, right? A bit.
Well, Sabine did make a video about how science is now there for making money. This is why a monetary system creates a bias. You can use the monetary system for good, or you can just create a company for profit and create a bias which will limit your ability to research the things that are beneficial for humanity. Okay, so
good times.
1 second.
Good times don't often make good quality of numerous things.
I'm not saying a monetary system is bad. I'm saying a monetary system is both good and evil, if you want to put it that way. It has both good and bad. Not evil. It's not evil. It's what people do. And then that takes me off on another squirrel with regards to AI. Ooh.
Yeah, we should probably.
You guys, I'm going to create a video about AI, and you'll have to wait because we're not going to cover AI. And I do want Connor and Daniel to be a part of that. Maybe we'll do that in the next podcast. By the way, this podcast was only supposed to be about 2 hours, and we haven't even covered the other topics.
Very typical.
But that's and just so you guys know, we've recorded 5 hours worth and then went on and talked for another 5 hours afterwards until we were falling asleep. We meet on Discord every Wednesday and to talk about matters of science and squirrels. If there's someone out there that's interested, it's not an open Discord channel. The way it works is you send me an email with your Discord username. I will send you a friend's request. We'll chat, and if it fits, then we'll invite you, and you can join us and become a tentative member of IRIS-AsteronX, and you can then participate by involving yourself with our chats. If you are interested in this, fantastic. Send me an email. It's under the About on YouTube, or you can find it in the contacts page of our website, astronx.com. Now, when you leave your comments below, please don't make them long-winded, because try to be short and sweet and efficient in your comments. I have a lot to do. If they're long-winded, I tend to gloss over them, and I may not reply to you. Lots happened. We're doing a lot of things. We're building a space project. And by the way, we have a lot of members. Some of them a lot more active than others. They're around the world. Not all of them are on the website. We still have to update that website. It's so obsolete.
Wait a minute. Am I on it?
So
Probably not.
Okay. I'd like to get back to this other half of the universe. Okay.
Yep. And I think your levitation ring or whatever propulsion system is what you were going to go on next, right?
Well, we're going to cover first. We're going to cover, and Connor, you let us know when you need to go.
Oh yeah. It's just at 5:30.
5:30. Okay, then we'll make 5:30 the cutoff point for the podcast.
Okay.
All right.
And I'm sure if we don't cover all topics that you had initially planned, it's good material for future podcasts.
Oh, absolutely. And I'm really having a blast here.
Yeah.
And just for our audience to know, we've gone through some hiccups. About 5 years worth of hiccups. And just fairly recently, my own mother passed away at the young age of 80 years, which I saw coming for the past 3 years. I saw it coming and prepared myself, and I tried to prepare my family. But when the day actually comes, there's no preparing for that. It's tough. We've gone through major changes. I know my mother would have said, it doesn't matter. I'm glad to have the kids I have. I'm sure that this is what she would say. And she would also say, son, take us into space in a big way. Humanity needs the frontier of space. Do it for me. Do it for humanity. And if you have to do it for me first, then do that. My mom was smart.
And regarding time travel, I would say back to her, I will see you again, and you will be in 2100.
Oh, you're squirreling me, Daniel. I'm gonna. We're gonna talk about that next podcast. But so I have to say, my mom has helped us a lot, and I've helped my mom a lot. I've pretty much have been her, in addition to creating a space project, I was her full-time caretaker, as I'm a half-time caretaker for my wife as well. Since the thing that we can't mention, the illnesses that spread around the world that I guess we can't mention on YouTube, it affected her brain. And so I've been searching wildly for an answer, a resolution, solution, which was also one of the reasons why I decided to create a department of biology and then a department of consciousness along with our engineering and so on and so forth. So, but I have to say, thank you, Mom. I miss you.
Yes. I'll see everyone in the future. I'm counting on it. Anyway.
Okay. Quantum.
Yeah.
Positive space, negative space. If I use this plane as the analogy, you can see this plane right here, right now. you can see this plane. There's an ambulance that just went by. I guess
We didn't hear it.
Okay, probably not. It was
Maybe
loud.
the recording did, but I didn't.
The recording might hear it, but it was loud. That's why I paused. I guess it was punctuating my statement. Okay, so
we have an emergency. Yes.
Yes, that's right. This plane represents what I'm about to state. When I say represents, this is a philosophy. This is why consciousness is so important. There's nothing, if you're going to engineer a starship or a new basketball or a rocket engine, you're going to use your mind. You're going to use your brain, which is your consciousness. You don't do anything on a daily basis without your consciousness. So how important is consciousness to reality and to a space project? Inseparable. You can't just pick up a banana, chew on a banana, and go hoo, 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 and think that you're going to go anywhere by taking your brain out of the picture. You're going to be a vegetable, so to speak. So the philosophy, I'm using this as an analogy. This is analogous, this plane, to separating positive energy from negative energy. So now, looking at this plane, watch what happens when I do this. Do you see the plane now? You don't. It's gone. And yet, there is this layer that exists, this metaphorical layer that exists between positive space and negative space. Boom, gone. You can't see it.
Yeah. It's like a fifth dimension or something, right?
Well, I'm giving it is kind of sort of like that, but I'm giving the analogy for our audience to understand that what separates between positive and negative is something that appears to be intangible. Appears. The key word, the operative word, is appears. So now, and yet it still exists. This perfectly illustrates. It both exists and doesn't exist. Kind of the Schrodinger cat. And how come you can have a Schrodinger cat? Because the reality, the strangeness of the universe is true. It's truer. The reality of the universe, the strangeness of the universe is truer than just pure mechanical. Every day, here's the ground. I can beat on the ground. I can throw my basketball. I can stomp on the ground, the floor. That's the mechanical side. The quantum mechanical side is what you cannot touch. You cannot see it. So when I was saying that around this ship, where is the negative half of the universe? It's on the other side of this membrane. You can't see it. You can't see it. But it exists. What you can see is not the separation. You can see the things that appear and disappear. Appear and disappear. Appear and disappear. Quantum entanglement is micro wormholes between two particles. What Einstein called spooky action at a distance which is later confirmed to be entanglement, which later is confirmed to be wormholes. Micro, very tiny wormholes between 2 points through positive space. So when they entangle two particles, do you see the wormhole connecting the two? No. And what is that represents, that wormhole? This right here. Can you see it now? No. I can use this and I can do something even better to illustrate that point. So if we hide this plane and I take this cylinder, take these end caps off,
the ship somehow looks more epic with the cylinder.
Yeah, it does kind of look epic, doesn't it? Okay, now you see it. Now you don't. Now you see it. Now you don't. So, and people are probably going, what the heck? You don't know what the hell you're talking about. This is crazy. It's because you're not understanding the metaphor. And that's why you don't understand it. It's a metaphor. It's not a literal thing here. This tube represents the wormhole between two particles. So imagine for a moment you got a particle on the right side and you have a particle on the left side. And this is the wormhole between those two particles, which is a very big wormhole, yes. But when you are in a dimension, so to speak, you can't see the wormhole. But if you were to go at right angles to that wormhole, so to speak, voila, you see it. And so the wormhole is actually a tube between positive space and negative space, half space. That is a conjecture. And I'm going to bet you that the math tickles it out to be correct. Aha. Aha. But the analogy here is still true. You can't see it. So if you imagine for a moment that this tube, if I go into a camera, this might be a great way to do it. So if I go into this camera and I get this tube to track my camera, and I'm on camera 1. So if I get it to track camera 1, and then I go to camera 1, I'm not sure this is going to work actually.
I see a faint shadow.
Well, here's the problem with the camera, why it's not quite entirely working, is because if I could really get this camera to be square on with the tube, you can see it's getting fuzzier and fuzzier and fuzzier. And not because of my clip, but because I'm zooming in so much that the tube begins to be so square on. Yeah. It begins to become so square on that the thickness of the tube, which is virtually nothing in Blender, we'll no longer see it. And that's, so yeah, it wasn't a very good analogy. It wasn't a good way to illustrate it. Okay.
Yeah, we're trying to
so when I do that,
illustrate higher dimensions in 3D.
yeah, when I do that, I'm I'm absolutely square on with a cylinder that has no thickness. I can give the cylinder thickness by adding a solidify modifier.
Is my
like that.
previous explanation correct, that we're trying to illustrate something in 3D that
yes.
is like...
Yeah. If the tube was actually 3D and made of positive space entirely, then you should see it all the time. You should see the wormhole. But because it's not, you can't see it. Yeah. It's in space between. It has no thickness.
For those who don't know what we're talking about, for example, the best show that illustrates this is not just Interstellar, but The Expanse. You know, in Interstellar, you had a voluminous, a 3D wormhole. In The Expanse, a 2D wormhole. Because those were the ring spaces.
How about Doctor Who?
Yeah. Well, then you are watching from the inside, and you're going all over the place.
Yeah. That's a similar analogy, because you can have a larger space inside, meaning you have a time bubble inside that enlarges your space relative to the outside.
Yeah.
You know, instead of being a British phone box, I thought it would have really been cool if it was a porta potty.
Why?
No, I'm just kidding. A porta potty.
I mean, it would be good on a road trip, but...
Oh no! I can imagine his enemies. Oh no! Anything but the porta potty.
Oh yeah.
I'm in keeping in theme with the British humor.
Yeah, I set them in there without the dimensional shift, the TARDIS effect, and then kick it over. Whoopsie! Now your enemies are in trouble. Yeah.
So.
Porta potty joke.
Yes, that's right. Kick it over. Yeah, that's right.
Yeah.
Oh boy. So there was one other point that I wanted to throw in, and by the way, you guys, this is a new ship design of mine, 328 meters in length by 84. 125 in overall width.
He loves big ships.
328 is not that big, really.
Oh, really?
But I do love big ships.
What if it was 10
aircraft
meters
carrier
or
size.
A couple... Yeah. What if it was 10 meters long? You know?
How big, if you want to put in perspective, right, using known technology, how big are SpaceX's rockets, right? They might not be super wide, but their length, the scale of those is massive.
Oh, SpaceX.
Yeah, I'm bringing SpaceX into context here, just because I think the question, right, was why are these ships so big?
Yeah,
and I think just intuitively, it's because going into space requires you to have a lot of materials and resources at the ready while you're in transit. You definitely need enough space, right, to carry and all of this stuff that you're bringing with you. And I'm sure a lot of that space is going to be storing the fuel for your engines, right?
Well, there's actually several reasons for this. And the main reason for the size of the ship is because, early radios, early televisions, components were not miniaturized.
Mm-hmm.
And as we begin to develop, look at what they can put in. They can put your entire cell phone inside your wristwatch, and two-way. A cell phone is a two-way communication device. I almost slipped up and said that. All that can be put into your watch. And there was a time when a computer was the size of a two-story building. Early mechanical computers. So this is not a Starship. This is a spacecraft, aerospacecraft, probably mostly intended for in-space operations, because, and I'll take a moment to make this point, this looks like it could land on a planet, and it might be able to, and it looks like it has vertical gravity, meaning like this little guy here. So he's 6'1". You can see this relative scale of this ship. So aircraft carrier size. The main reason why spacecraft, I'm not talking about rockets just yet, the main reason for spacecraft being so voluminous, big, especially a Starship, is it's mostly components. It's mostly the space inside is for the drive. And yes, you're right. Fuel, propellant, systems, life support, waste management, I'll just sum it up and say life support systems, batteries, capacitors, power bus, conduits. I mean, you just name it. There's so many things that have to go into a Starship. Where are they all going to go is ultimately, if this was a Starship, or even as a spacecraft right now, this craft, the actual space that humans would take up, would be the size of this cube that I just dropped in there. So there you go. You guys get comfortable.
Well, yeah, that's a bummer. And
the rest of the craft is system. And if I take and I put in another illustration,
I second that. I think that would be just your private spaces. But people have to be able to crawl into the other parts of the ship, right?
Yeah,
so that's
of
technically
course.
Habitable volume.
Yeah.
As well.
Oh, yes, of course. So I think our audience is smart enough to know that. But if I illustrate my crude, and no, it's not obscene. Come on, you guys.
Yeah.
If I take and I make a basic, if I make a basic rocket, I'm trying to make a nose cone. Let's say something like that. And then at the bottom, I do
whatever. I don't know. I don't expect you to put an engine nozzle there.
You don't expect me to do so? Oh, bloody hell.
Yeah, because some rockets don't have that. Some rockets have all those things hidden away inside, and
this rocket's not. I mean, this is just your basic. This is just your basic monkey rocket.
Yeah.
Okay. So
That's a booster.
yeah, it does look like a booster. let's pretend for a moment. Let's have moments of fantasy. Let's pretend for a second that this poorly illustrated rocket, we'll make the bottom that base color, and then we'll make the top. And the reason
you are in the converging cone at the top at most.
This is the payload at the top. And inside the rocket is something like something analogous to this. I'll separate it with a band of color, which when I zoom out you can't see. But at the top is the payload, and some maybe avionics. Right in here is, say, your oxidizer. In fact, I'll do one better. What I'm going to do is I'm going to make this blue oxidizer, and at the bottom I will make this the fuel. Okay, so when a rocket goes up, not a booster, a rocket, the majority of this rocket is fuel and oxidizer, the vast majority. If I take this and I flip it on its side, the analogy, you guys begin to see that this rocket and the spacecraft, you guys can understand that. Wow, that really distorted.
Yeah.
Oh, I don't know what happened there.
Yeah, that rocket's toast.
I guess it must have had a failure. You see, 1 out of every 600 rockets fail. I just proved it right there in Blender. I'm serious. No, I'm not serious.
Oh, yeah.
It is true, by the way, the statistics are valid that 1 out of every 600 rockets have some sort of failure, whether it's major or minor.
Oh, okay. Yeah, of course. But we have so many engines now that we just don't care.
It's not the engines per se. Okay, this rocket, the SpaceX rocket, which Elon has already, the Starship rocket, which is yet to come to total fruition, has already illustrated that up here in the nose cone is the living space. Well, you know, that's the same thing, basic thing as what I just illustrated here. Here it is, right there. There's your living space. Up in the very nose will be the living space. The rest of it is necessary. And the audience probably is thinking, why? I mean, why is it that way?
The audience is like, I thought we were trying to get rid of the rocket equation. We were to something better.
Well, the reason why it's that way is because efficiency. Now, this is an important point for our audience. Efficiency. The detonation engine, which I talk about in the video I just posted a couple of days ago, has a specific impulse greater because it's a detonation engine. A detonation is more efficient than a deflagration combustion, which is subsonic burn. Deflagration is subsonic, and detonation is supersonic. Now, the difference is efficiency, conversion of energy, fuel, oxidizer, and energy released. So why the Starship rocket or any rocket is mostly fuel and propellant is because its efficiency, it's powerful, but not very efficient. It's burning through its fuel and propellant too rapidly. So one Starship or one Falcon Heavy with its boosters can reach Leo, but when it reaches Leo, low Earth orbit, it's dead. It needs to be refueled. So, yeah, Connor, that's fine, no problem.
Okay.
Just for our audience to know, Connor sadly will have to go.
Yeah.
He has to keep his time travel up. Okay.
Oh, yeah.
So, efficiency for our audience here. This is why a spacecraft, this is why the habitable space is a tiny little space. Even on this rocket, the very tippy tip of this nose of this rocket is where you are cramped. This is your sardine can right here. This is your sardine can right here. Because of the efficiency of the engines is too low. Now, if this was a nuclear engine on the back of this rocket, if it was nuclear, then you have something different. You have an efficiency.
Or even a detonation engine, which seems to be better than nuclear, right?
If this was a nuclear light bulb engine, which does not spray out radioactive, there's no beta, alpha, gamma particles coming out of it. A nuclear light bulb engine, and that's one of actually hundreds other engines that are anetronic. But a nuclear light bulb engine, which has been tested and proven to work, has a specific impulse great enough that you can basically mount one engine to the bottom of this 328 meter ship. One engine can go up to Leo, then to high Earth orbit, Io, to Mars, and go to Mars in 1 week, orbit, deorbit, return and orbit Earth, and land on the surface of the planet, all with one single engine. Because
you
gotta go. Yes.
Yeah. Let you guys know I'm headed out here, but I look forward to our meeting next week.
Absolutely.
I'll see you guys there.
Okay. All right. We're going to miss you, but we'll get you in on next week's podcast.
Yep. I'll be there for next week. Bye-bye.
Okay, Connor. Cheers.
Cheers.
Yeah, I have an appointment.
Yeah. Connor has an appointment that he needs to keep. So, efficiency of engine is why the Starship rocket or the Falcon Heavy, or why so many of these other spacecraft are limited to the size relative to the components.
On the size habitable,
Yeah. So if we have a propulsion system that's more efficient, what that means is that we could technically have
more volume for humans.
Theoretically, if we're advanced enough, if you were to take this ship I have here of my design, which, there's other ones out that are very similar to it. It's an idea. I was inspired by another ship that's kind of sort of similar to this. But if these engines were efficient enough, then everything contained within these engine nacelles is all you would need. The rest of the ship could be habitation. That would be we would have to be sufficiently advanced to do that. And of course, we're not there yet. We're striving for that.
Yeah, I would love a healthy balance. Like the first half of the ship.
Yeah.
Being habitation.
Although I would be happy with all this rear portion. I mean, having all the front, and you know why we picked the front? Because the deflection arrays. Where's the safest place on this ship? It's the nose. Where the strongest portion of the deflection array is up here around the nose.
Assuming they don't fail, right?
Well, if they're going to fail, you have a lot to worry about. It doesn't matter whether you're here or back here.
We're going to have the same sort of thing, regulation-wise, that airplanes have with ETOPS. We're going to have a number of these things overlaying each other that each can do the job, right? Yeah. And the chance all of them fail is zero.
Redundancy. You're referring to redundancy.
Yeah. Unless you're making dumb mistakes like Boeing has, right?
Well, I'm not saying, I'm not going to say any names or, I don't think we should. Let's not polarize.
It's not polarizing at all when you see a 787 taking off and its engine shut off because of some glitch.
Okay. We know that there's been some issues with, and we expect it because, one can argue that once a week, every vehicle should be go through a routine maintenance inspection.
Well, they do every time they land, but
no, they don't every time. It's based on hours in flight. But
airplanes
automobiles should undergo the same rigorous inspection. Then, if it happens that way, then we kind of get into this problem where, who can really afford their vehicle to be inspected? Now, if something happens and they're injured, then one can argue, how can we not afford? Because the medical costs, or even worse still, someone passes away because of an injury. Crash. Or they're left somewhat maybe mutilated. It looks like he's saying, my character here looks like he's reciting some, what is it, the famous quotes by, it doesn't matter. You guys will probably get it. The famous...
the character looks like the Eldridge from the MCA Hogarth series, except he's way too human-shaped rather than elongated like for low gravity.
I picked this character because there's some similarities to my own appearance.
You are a high gravity accustomed from that series, Eldridge, which has white hair. Well, I don't know why they call
as
them
you know, my Discord image is a better depiction of my image. But anyway, we're not talking about me. Yes, and anyway, walking around on a 328-meter ship here kind of gives you a great idea. This is why, in case you guys are wondering why I put an HDRI and why I put a ground, and then I make my ships to literal size, is because I want to be able to do this. And then it gives me an idea. I'm kind of designing my ships partly this way. Yes, I could crunch the numbers, but that's only half the fun. Designing the ships this way gives me the ability to visualize the ship. Then I can use the numbers
Mm-hmm.
And I'm doing what we call engineering by means of swag. And for those of you that don't know what a swag is, it means scientific wild ass guess. That's what a swag is.
Yeah. So you are the wild ass guess is not just some random stuff, because you kind of know what approximately the size of everything has to be, and the math just refines it. And when you're walking around like this, it doesn't seem big at all. It seems like a Corvette, like a small ship.
Well, if you've ever taken the tour of an aircraft carrier or been stationed on one, you'd have an idea of what I'm talking about and what I'm doing. And you can look around and go, wow, it doesn't feel, on one hand, it doesn't feel so big. And on the other hand, when you're walking along and let's say you walk up to the tower and you go, wow, OMG, that's an engine. I can walk inside of that. Then it kind of feels big. I mean, there we go, right there. There's the guy. Yeah. He's 6'1", and
he's a millimeter high.
Yeah,
from here.
Yeah, he's a nanometer in scale relative to the ship. Is what it feels like.
Oh, bang.
Yeah.
So you want to get to the engine because there's an emergency. Well, if you're a human and not a cheetah, it's going to take longer. Right?
I mean, look at this. This is ridiculous in scale. I love to do this. And down there is the door, which I will be mounting on the side of the ship. And the door is the opening from top to bottom is it is 2.3 meters.
Yeah.
In total height. So 2 meters is 6'5", about 6'5".
Yeah.
And this is 2.3 meters in height. By 1.9 meters in width opening. And you can you're seeing the housing. You're not actually seeing the door, let alone the handles to hold the door. So that'll give you an analogy. In fact, if I take the door...
just a question though. The propulsion system your guy is standing on, we're going to be talking about that next, right?
We're going to touch on it. Yeah, we're going to touch on it. There's the door right there. So if we'll touch on it.
Looks half robotic from here. Wait. You're designing it so you could actually step on the propulsion ring. This would be an actual position.
No.
The door?
No. It's whoa!
No, you don't be an idiot.
My character almost met his maker. Okay. I was trying to get it.
Yeah, you need some railings there now when it's...
Yeah. Okay, so technically speaking, and I'm glad that you asked, the door...
Sideways.
This is a vertical... This is a vertical gravity craft.
If the craft is under thrust gravity, then this is a skyscraper now.
Correct. So for those out there, what Daniel just said is correct. For those of you out there that are kind of unfamiliar with what we're talking about, if I get this into position, well, this is just a roughing in, but essentially,
Todd, is if you have a design like that, then having reverse engines would be a good way to get a concussion. So I would rather do a flip and burn then.
So here is this is the gravity of the ship is vertical.
Yeah, your reverse engines are probably going to give everyone a concussion. So if it's that design for the interior, then those reverse engines probably got to go.
No, no, the engines, the way I'm designing this ship is that the engines do this. And
why do you need two of them?
The reason why you have forward engines and rear engines and side engines is because if you are in a heavy load, you want to jinx. And jinxing is rapid maneuvering. You want to steer the ship, you want to slow down, and let's say that you are needing to maneuver this ship rapidly. You want to be able to come to a quick stop. And what Daniel's referring to is, well, the squishy bits inside are going to, that can't be... They're going to
race forward.
That can't be any too good, is it? I mean, it's just not going to be good enough for us to do. And
it'd be disorienting for one. If you design the ship with two floors, the ceiling is a floor and the floor is a floor. But that would be disorienting.
No, you're looking at it incorrectly, because and so our audience understands better.
Yeah.
I'm trying to get this.
That's when you're flying.
I'm trying to get this just perfectly.
Also, how uncomfortable it would be to land on a planet if in a ship that is a skyscraper design.
Well, you're not going to land. You're not going to land on the ground like this. You have to have some sort of gimbal system. Okay.
Yeah.
So, what's up? What is up with? How is this possible? Mass reduction. That's how. So with mass reduction, we greatly minimize this this problem we would have with when we decelerate. Early mass reduction, which we've already have proven, we're at the beginnings in lab. They've managed to have some degree of success. Our understanding is greater than the actual engineering right now.
Takes time to get into practice.
We will have to get back to this so I can post links to the relevant information. But even certain agencies have been looking into this. What mass reduction will do for us, and this is what's important right now in this podcast, is it won't reduce all of the forward acceleration, or all of the forward deceleration, I mean, and it won't reduce all of the forward acceleration. But what it'll do is it'll mean that instead of experiencing, say, 3 or 5 Gs, you might experience a half G deceleration. You might have to experience a little bit of temporary deceleration. That's what mass reduction means for now. And
mass reduction,
but now,
which means force is the same, then acceleration, and if mass goes down,
elevator.
Acceleration must increase. Then force equals ma, right?
Yeah, and what astronaut, when you're in a rocket and you accelerate, you're accelerating, like, I think up to 3 Gs. And if you're in an elevator and it goes up you're experiencing an increase in relative gravity.
Yeah.
The way we could do this ship two ways. We can accelerate, and your gravity would be at your feet.
Yeah.
Because you're
So
traveling.
essentially.
Hold on.
Essentially, okay.
Or we could, when we get to our destination, we can spin the ship around and go backwards. But either way you look at it, you still have, if you're decelerating, you still have gravity. If you're accelerating, you still have gravity on your feet relative to your head. So it's doable. This is still doable.
Yeah. And here's the thing. Anyone who can't comprehend this, if your mass drops by 2, I use simple numbers, okay? Your mass drops by 2, but your engines still have the same, let's say, kilonewtons of thrust, maybe meganewtons, okay? Then your acceleration must double, but since the force is the same, you're experiencing the same force, but at what seems to be a reduced mass. So for you, 2g feels like 1g, right?
Yeah. There's another thought I just had here. If this ship was to maintain orbit around the Earth and not go too high, say a low orbit, and you were in geosynchronous with the Earth, if you're not too far away, you're going to experience 1g gravity on this ship. If it's parallel to the surface of the Earth, you will have vertical gravity.
Yeah. Yeah, of course.
I mean,
you'll have
horizontal gravity. I'm sorry, relative to the plane of the Earth. In other words, like you're still going to be, you'll be standing. It'll be as though you were standing vertical gravity on the Earth, as opposed to horizontal gravity in the ship. So, if the habitat inside was on a rotated, so if you're on if this is landing on a planet, then the habitat would rotate and you would step out the door just like you were on a just like I had the first time a few minutes ago.
Yeah, you would have a bit less because you're farther from the Earth, but it's still a sizable percentage of Earth's gravity remaining at geostationary orbit, right? And if you have the ship vertical, like a vertical icicle, like an icicle, well, ship's under gravity. Then, or the end of it may have a little bit less, but because it's just one special height. The part below it, below geo, would be a little higher, right? If you're steady, you can have a space station at geo, right?
You can have a space station that has, if you were to make a space station at low enough orbit, then you would have 1g on the space station.
Roughly speaking, I mean,
you would have
do the
1g
how far
without it rotating. You would have 1g. If you had it would have to be in geosynchronous orbit. But here's the way you would do that: is you would put a ring around the planet that would maintain an equidistance from the surface, and it would not come down to the planet. If you sent tethers out to, say, high Earth orbit, those tethers could be used to counterbalance your space ring, your space station, and you would stay relative orbit to the Earth The Earth would be pulling on you, and so too would be the tethers out into space. No connection to the planet's surface whatsoever would be applied, would be there. You wouldn't need it. So, you can tether to space. You can Google it. You can research. The numbers have already been crunched. By the way, probably the world's leading experts of space elevators is Japan, by the way, a company in Japan. Believe it or not, a construction company, the largest construction company in Japan, also specializes in space elevators. Who figures? I think it's perfect. The materials,
this would be like a space elevator ring or something like that.
We actually now have the technology capable of producing a space elevator. It's within our technological means now. This is exciting, but there is a big problem, because if you run a physical elevator from the ground to space, pass through the various layers, it will ground to the Earth. NASA already proved by putting a tether through the exosphere, it vaporized the tether. There's an electrical potential. Nikola Tesla's talked about this. There's a potential energy gradient that will vaporize. And if it's tethered to the ground, you may vaporize, you may take a divot out of the ground equal to 100 kilotons. So,
because
not good.
There's ions. The sun is energizing the upper atmosphere, right? And it's causing enough energy that can run an electric current down through the cable to the earth, to ground.
Well, it's like a bolt of lightning is what it would be.
Yeah.
Much more force.
You could put Kapton shielding on the cable, but if you have a failure, boom. Right?
Okay, so there's limits. There's things that need to be worked out for a space elevator. But just so the audience knows, the technology now exists. Nanotubes. And China invented a technique to make long nanotubes, which are far strong enough. The next limitation with a space elevator is debris, satellites. No doubt, if war takes place, it's not November yet, but if war took place, it's likely to erupt into space and create a Kessler syndrome, which Kessler syndrome, for those who don't know what that is where one satellite is damaged. It breaks into pieces. Those pieces fly out, slam into other satellites that are unable to move, or at least move fast enough. And then pretty soon you have a cascade event that erupts into a Kessler syndrome, a near total smashing of telescopes, and not telescopes, satellites breaking apart, because our material science is so weak and feeble that when you have particles slamming in at high speed to other particles, it's just going to smash them apart.
It's not really to me about feebility. The feebleness, because look, it doesn't matter if it's indestructible materials these satellites are made of. Knocking into each other will damage them regardless. It will turn the settings inside to liquid or mush.
It's important. The material science is very important.
It would help contain the Kessler syndrome, but the satellites would be dead anyway, and especially anything inside.
Again, material science would negate. It wouldn't make it so easy for the satellites to be dead.
Yeah.
Well,
Well,
anyway,
breaking up would be different. Would be not happening as often, but it doesn't. So
yeah,
so in my many years ago, I collided with an old car. You know, it's made of steel.
yeah.
It was a Warburg, right? We collided with a modern car and absolutely demolished one of its doors. Okay,
Oh, yeah.
we got shooken up so bad. The modern car didn't get shaken up because it was designed to crumple. This is why failure sometimes is better than being impenetrable. So I
You
have
mean
my
built-in failure? Yeah. Well,
I
in
have
that
my
regard, I agree. Yeah.
I have my doubts that making a ship unable to be penetrated unable to be crumpled and stuff is a good idea because
Yes.
everything else inside will be thrown around.
I wasn't
If
referring to that, but yes, you're correct.
Yeah.
To illustrate what Daniel's talking about, a number of years ago, I saw a 79 Cadillac and a 84 Honda Accord try to blend, ran into each other. The Cadillac, it bent the bumper on the right front corner somewhat. It had impact shocks to cushion. That's at that year there were bumper shocks, but when I turned and looked at the Honda, it's the engine was nearly inside the passenger compartment. There was almost no front to the Honda. But here's the thing.
So here's the thing. Do you want to be intact and dead, or do you want to be fallen apart and alive? Okay.
The person, the guy who got out of the Honda was shaken up and uninjured. The woman in the Cadillac broke her wrist and smacked her broken nose and broken wrist, smacked her nose into her steering wheel. And the reason for it is because the Cadillac was much more rigid of a vehicle. The Honda was designed to concertine, to crumple, absorbing the energy of the impact. The shocks on the bumper of the Cadillac, well, it was too old. The shocks should have been maintained. They didn't really compress correctly. They compressed instantly and right into their limit, which hit solid metal, which is a relatively large subframe. I think the Cadillac was a unibody still, and not a solid frame for 79. I'm not sure about that. But as soon as that bumper hit that solid framework, that rigid, more rigid relative to the Honda, it didn't give anymore. The bumper twisted slightly. Just, you could almost buff it out type of statement. And that's what caused the Honda to crumple. But it transferred that shock wave to the squishy bit, the driver, and sadly, she was injured. But the guy in the Honda got out. He was okay, thankfully.
Yeah. So trade-offs. For satellites, you don't want them falling apart, but for human vehicles,
I think
you don't want them to be immovable or impenetrable. Right?
Yeah, but now what I was referring to with regards to the more rigid material is that it's like the material around these engines on the ship and the engines themselves. If micrometeorites slam into these engines, the engine says, I don't care. You don't even faze me. The fury that comes blasting out of this engine, the engine says, the material, the alloys, the material or alloy, whatever it is, says, I don't care. Have at it all day long. You could even have the fury of fusion inside this engine, and the material of the engine says, okay, it's a little tickle, but hey, keep it up all day.
Physics, Todd, physics. What kind of material is the engine cone made of other than normal material that is charged in a way that when a micrometeor comes in, tries to move the material, and you have lens forces fighting against that, and it prevents the meteor from making a crater.
But there is
in other words, polarized hull plating.
There is no squishy bits in a satellite, so it doesn't matter. You can, the whole thing can be of a rigid material.
Yeah, but will there be a crater, or will it be a polarized hull plate? Because Enterprise from Star Trek Enterprise, they had polarized hull plating.
Well, just for our audience to know, this has been proven in a lab already. If you take something like a piece of graphene and you charge it with just electrons, and where the electron density on the surface of the material reaches a critical point, then guess what? You can hit it with a laser, and it won't do anything. You can throw a projectile at it, and it won't get through. And the reason why is for the same reason that in the particle accelerator, how they can use an electron gun to accelerate a particle, which we will save for another video. And by the way, on that, Daniel, I think we should conclude this podcast. Well, we've been talking for a while. I need to take an intermission here. So
okay. Yeah, we can talk about the other items. It's probably going to be.
We'll get to the levitator. Magnetic levitation is what the levitator is, so you guys know. That's what this disk is in the ship. It's magnetic levitation. We will talk about that, what that means, how we do it, so on and so forth, plus the coming videos that I'm creating. The one I just posted is an example of what's to come. And on that note, I want to say to our audience, thank you. If you've been with us all this time, excellent. Daniel, say cheers to our audience. And
cheers, guys. Hopefully, this human conversation is well to your liking. And we would, of course, like to cover more topics in the coming weeks, including the full gamut.
Absolutely. Oh, we look forward to it.
Well, it's like, based on what we have done today, it's likely going to be one main topic and then a whole bunch of other side roads. Right?
Yeah. We squirrel a lot, but the squirreling it's wonderful. It is what makes our conversations so unique, and two, because we're a bit of polymaths, and three, being well-rounded is better than being strictly one specialized for what we're doing. There is a place and a purpose for specialization. If you can be both a polymath and a specialist, that's better still. Okay, so I'm going to conclude by doing this. You guys know what I'm going to say. Until next time, keep wondering about space. Thank you. Cheers.